Hello everyone, welcome to the next lab of ECE573 Advanced Embedded Logic Design. In this lab, we are going to discuss about the HLS Pragmas, mainly data flow and dependence Pragmas, and then we'll discuss about the implementation of the fast Fourier transform F50 algorithm using the SDSoC. In the previous lab, we have discussed few of the HLS pragmas highlighted in the red color. Here, we'll be focusing on latency, data flow, and the dependence pragmas. Okay, so let's start with the HLS latency pragmas. So HLS latency pragmas specifies a minimum or maximum latency values or both for the completion of a function, loops, or region. Okay, so via these pragmas, you can tell the tool that this function should be completed within this minimum or and maximum latency values. Okay, then tool will try to optimize your code so that it meets the desired latency constraint. So what is the latency? So here you can see in this format here you can mention the minimum and the maximum values, and both are the integer value. So what is the latency? Latency is the number of clock cycles required to produce an output. In case of the function, latency is the number of clock cycles required for the function to complete all the output values and return. Okay, so that is the one complete execution of a function. In case of the loop, the latency is nothing but the loop latency is equal to the number of clock cycles required to execute all the iterations of the loop. So by default, as we know that HLS tool try to minimize the latency in the design. So by when you specify the latency pragmas, you are going to specify the minimum and the maximum value. So what the tool does in the regular without the latency pragmas, that it will find out all the possible implementation of your algorithms and then choose the one which gives us the lowest possible latency. Now suppose that you have specified the latency pragmas with the minimum or the maximum value of the latency. And in the then what the tool will do? Tool will again find out the possible implementation, and if the tool does this sequentially. So tool will go to the first option, then we'll find out what is the latency, then the second option, and so on. Now suppose that you have already mentioned that this is my minimum latency and this is my maximum latency, and if the first option or first architecture which tool has generated has the latency between the minimum and the maximum, in that case tool doesn't no need to do any further optimization. Tool can stop and then give you the corresponding output. Suppose that you have specified the minimum and maximum values, but the tool is able to come up with the architecture which has the latency less than your minimum value specified. Then here what the tool can do? Tool can make sure that it will increase the latency between your minimum and the maximum value by doing the resource sharing. So that means it will reduce the resource utilization so till the point that your latency is minimum between the minimum and maximum. As we have discussed before, the latency and the resource utilization, you always get a trade-off between them. So if you try to reduce the latency, you will get a higher resource utilization, or if you try to reduce the resource utilization, you will get the higher latency. So once you meet the latency criteria, and suppose that your latency is much better than the minimum amount the customer wants, then the tool will try to increase the latency so that it is between the minimum and max value, and see if we can do the it can minimize the resource utilization via resource sharing. And the third problem is can be that your latency is greater than the maximum value. So in that case, tool is not able to meet the latency constraint specified by the user. So in the tool will try all the possible combination to see if we can meet the latency constraint. If it fails, then it issues the warning and produces the architecture or design with the smallest possible latency, achievable latency in excess of the maximum latency, because you are not able to, tool is not able to find the design which has the latency lower than the maximum latency specified by the user. So you will get the warning. So what is the use of this latency pragma? So latency pragmas can be useful when you are sure that what is your latency requirement, and by putting that requirement in your code, you are helping the tool to minimize the runtime. Okay, so because when you specify the latency constraint, then the tool has to search for the design with the specific latency between the minimum and maximum value, so the number of possible solutions can be reduced, and that will improve your runtime. So for example, in the left hand side, there is a function foo, and here you are telling that this function needs to be executed between the 4 to 8 clock cycles. So this is the requirement given by you to the tool. While in the second one, you are telling the tool that this loop 1, you want the latency to be maximum 12. Okay, so you need to make sure that this loop is executed within the 12 clock cycle. Okay, so this is the how you can instruct the tool that what is your expected latency of a particular function or particular loop. So in addition to the HLS latency, there is an additional function called as the HLS loop trip count. Okay, so for you, the homework is find out the difference between the HLS latency and HLS trip count, and what is the how they are helping the tool and the user to get the desired functionality. So this is the homework for you. So now from the HLS latency, we'll move to the another pragma which is called as the HLS dependence. Okay, this is again another useful pragma. It provides the additional information that can overcome the loop carry dependency and allows the loop to be pipelined. So as we have seen, the pipelining gets affected when you have the dependency between the iterations of the loop, or even sometimes it gets affected when you have the dependency in a single iterations of the loop. You cannot execute the next instruction unless the previous instruction is completed. So there are certain dependencies are there. In some cases, dependencies are not there, but the way you write the code, the tool assumes that there is a dependency. And in that case, you can provide the additional information to the tool telling that there is no dependency here, or there is a dependency here, take care while designing the architecture. So this means using this pragmas, you are giving the additional information about the tool, whether there is a possibility of the dependency or not. So there are two types of dependency: loop independent dependence. That means in a one inside the single loop, in a single iteration of the loop, there is a dependency. That means same element is accessed in the same loop iteration multiple times. Okay. Then there is a loop carry dependence. That means there is the same element is accessed in a different loop iteration. That means the one element is accessed in the two iteration. That means unless the previous iteration is completed, you can't execute the next iteration. Okay, so this is called as a loop carry dependence. In the most of the tool, they are designed to be more conservative. That means they will say that they will always assume that there is a dependency. Okay, so it is very difficult to develop a tool where the dependency can be automatically filtered out. So usually tools are conservative, where they will always assume that there is a dependency. So as a reader, you need to mention that if there is no such dependency, you need to explicitly mention it. For example, on the left hand side, you can see that you are first writing to the A of I, and then in the same iteration of the loop, you are reading from the A of I. So it is called as a loop independent dependency. So inside the one iteration of the loop, there is a dependency. So you can't interchange these two lines. Then here you can see that there is a loop carry dependence. So there is a dependency on the between the different iterations of the loop. So when you mention and when you give the additional information to the tool that okay there is a dependence or there is a no dependence, make sure you are giving the right information, because if you give the wrong information to the tool, then your architecture will be wrong. The output of the HLS tool will be wrong. So you need to take care that whatever the information you give to the tool, it's a accurate information. So what is the syntax? In the syntax, you can see that you are mentioning HLS dependence. You are mentioning the variable name or class. Then what is the type of the dependence, direction, then distance, and whether the dependence is true or false. For example, variable and class, they are either one of them you need to mention. You need to mention when you mention the variable, you mention about which variable you are talking about when you talk about the dependence. And or you can mention the whether it's a class of the variable, whether it's an array or the pointer. Then what is the type of the dependence? That can be intra-dependence, that is dependence within the same loop iteration, or it's a interdependence, dependence within the different loop iteration. Okay, that is the intra or the interloop dependence. So you need to mention what kind of dependence you are talking about. Then direction, what kind of dependence is there? Whether it's a read after write, or write after read, or write after write. So you need to tell the which kind of dependence you are talking about, and whether the dependence is true or false. So you can mention, given the tool, that this dependence is true, or you can tell the tool that this dependence is false. So usually you mention you use this pragmas to tell the dependence is true, because by true dependence is false, because by default the tool assumes that there is a dependence. So usually you use it to mention that there is no dependence. And the distance, here you mentioned that the suppose that you have the dependence between the different iterations of the loop. Okay, so in that case it may be possible that there is a dependence between the first there is a dependence between the each iteration of the loop, or there is a dependence between every other iterations of the loop, or dependence between the every second iteration of the loop. So that can be specified using this distance parameter. Okay, so this is useful only when you have the dependence between the different iterations of the loop, that is the loop carry dependency. And here distance, you can mention it, what is the corresponding which of the iterations are dependent on previous iteration. Okay, so intra dependence, so when the dependent is false, that means there is no dependence between the single iteration of the loop. Okay, so what is this means? That means you can move the operation freely between the one iteration of the loop, so that you can improve the performance of the area requirement further. Okay, if you mention that if you don't mention anything, that means the tool will assume that the dependence is true, and in that case tool must perform that operation in the particular order. So by using this pragma, you are telling the tool that there is no dependence. So that means the dependence is false, and then tool can then take the decision to optimize the order in which all the operations in that loop can be executed. So the next one is the interdependence. So here we are talking about the dependence between the different iterations of the loop. So when the dependence is false, that means there is no dependence between the iterations of the loop. Then you can see that the operation between the different iterations of the loop can be performed in parallel when you use the pipeline or the unrolled pragmas, so that the next iterations of the loop can be started earlier before waiting for the completion of the previous iteration of the loop. There are three direction pragmas. One is the raw, that is the read after write true dependence. That means there is a dependence where the write instructions uses a value used by the instruction. That means read after write. So that means you cannot do the read operation uh, before write operation, right? So here we are talking about the read after write. That means you are um, reading the value which is written by the write instruction. Okay. Then there is a write after a read dependent. That means here the read instruction gets a value that is overwritten by the write instruction. So here you are doing the write after you have done the read operations. And the last one is the write after write. So here you have the two write instruction which are writing to the same location in a certain order. And if there is a dependence, that means you cannot change the order in which the write operation is being done. Okay, so in case of the read after write, you are doing the read operation after you perform the write one. So you can't, since you are doing the read from the location where after you perform the write operation, that means you are using the latest value. So you can't do the read before write. Similarly, write after read, that means you are reading the value from the location and then you are performing the write one. So you can't do the read operation. You can do the read operation after you do the write operation. Okay, and the write after write is simple to explain that you are writing into the two location using the two separate instructions. So you need to execute them in the certain order. So we'll discuss the usefulness of this dependence pragma using the suitable example later. Before that, I would like to discuss the HLS data flow pragma. So HLS data flow pragma is similar to the HLS pipeline pragma. So if you discuss if we discuss before, in case of the HLS pipeline pragmas, we added the pipeline pragmas inside a loop or inside the function. Okay, so this is used to pipeline a function or pipeline the corresponding loop. Now, HLS data flow pragmas enables the task level pipeline, so allowing the functions and the loops to overlap in their operation. So if you have top functions has say three functions A, B, C, then if you don't use the data flow pragmas, then the A will be executed, then the B will be executed, and then the C will be executed. By using the data flow pragmas, it is possible to initiate the execution of the B before the completion of the A. Similarly, it is possible to initiate the execution of the C before completing the complete execution of the B. So this is called as a task level pipeline. So the functions or loop that accesses the arrays must finish all the read and the write access to the array before they complete. Okay. This prevents the next function or the loop that consumes the data from starting the operation. For example, you have the function A and you have the function B, and the function A is operating say on an array A of size say 256, and the output of the function A is given to the another function B, which is also using the output of the function A of the which is the array of size 256. So in the regular implementation, you cannot start the execution of the function B until the function A completes its execution and writes the output at all the 256 locations. So you need to wait for the function A to write the values at all the 256 locations of its output array before you start the function B. Now, in some cases, it may be possible to start the function B as soon as the first output of the function A is available. And this can be enabled using the HLS data flow pragmas. So the data flow optimization enables the operations in a function and the loop to start operation before the previous function or loop completes its operation. So that means if you consider the example A and B, then it allows the B to start the operation before A completes the writing in its all the 256 location. So it improves the concurrency as well as throughput, because you will be able to complete the operation in the fewer clock cycle. So if you take the example here, you have the A, B, C functions. Without the data flow, you will be first doing the A, then doing the B, and then doing the C. But by using the data flow, you can initiate the B before completion of the A if it is possible. Similarly, you can initiate the C before the completion of A and B if it is possible. Okay, so there you can use this data flow pragmas. Okay, so now we are going to discuss the HLS data flow as well as the HLS dependence pragma for the image histogram example. This example was given in your one of the quiz or I think the mid-sem question paper, and we will discuss what are the possible solutions to that mid-sem paper. So if you look at the histogram, you get the image. We can convert the image into the 1D image of say input array, and then you check the values of the each pixel, and then you have the histogram which find out how the pixel values are distributed. Okay, so histogram models the probability distribution of a discrete signal. So given the sequence of the discrete input values, histogram counts the number of times each value appears in the sequence. Okay, so you can see that suppose the input is each value is 8-bit, that means it can be if the positive integer, it can be 0 to 255. So the histogram finds out how many times each value has been occurred in the input. Okay, so how many times the G pixel value was 0, how many times the pixel values was 1, and how many times the pixel values were 255. That count is given by this histogram. So in the simple one, you can see that I have the input. I'm reading the one sample of the input, and then I'm calculating the histogram of the corresponding input size. So what I did for every input one, I stored in the local value of the input samples, and then I use that as an index to that histogram array. So whenever the input value is 0, the 0th is incremented by 1. And you can see the right hand side architecture of the corresponding histogram. So the problem here is that there is a dependency. That means you can see that in each iteration you are reading from the particular location from the memory, and then you are writing into the same location of the memory. So what is happening? We are reading from the hist array and writing to the same array in every iteration of the loop. And what this means, your pipeline, HLS pipeline initiation interval will be more than 1, or it will be at least 2, because you are doing the read and write from the same location of the array. So the initiation interval is 2 due to the read and the write dependence. For example, in the first iteration of the loop, say that you are reading from the location x0 from the array. So you can see that this value is say x. Then you are writing it to the same location, which is x0. So you are doing the read as well as write into the same location. So we know that the iteration for the latency for the one read is 1 clock cycle. That means you have to complete the write operation in the subsequent clock cycle. So this means you have the need a 2 clock cycle latency. Now assume that in the next iteration for in of say 1, it is equal to x1. Okay. So both x0 and x1 are depend upon the input, and which you don't know. Okay, so in the worst case, what may happen? Your x0 is equal to x1. Okay, so that means what will happen? You cannot complete the execution of your second iteration of the loop before you complete the first iteration of the loop, because in the first iteration you are reading the hist of x0, and then you are writing it to the hist of x0. And in the second iteration, again, since x0 is equal to x1, you are also reading from the hist of x1, that is hist of x0. So you cannot perform the read operation of the hist of x0 or hist of x1 unless the previous write operation is completed. Okay, so this is the main reason why the initiation interval is 1. So what are the solution? Okay, so say that I told you that the x0 is not equal to x1. That means I told you that when you are receiving the image pixels one after the another, your image pixels, at least that the subsequent consecutive image pixels are not identical. Okay, so in this case, you can see that there is no dependency between the different, at least the consecutive iterations of the loop. That means we know that we are telling that the x0 is not equal to x1. That means there is no read and write dependency. So in this case, this code, if you write this code, you know that this dependency is not there, but you need to inform to the tool, because the way you have written this code, a tool always will assume that there is a dependency between the read and the write in the subsequent iteration, and tool will give you the initiation interval of 2. So by using the HLS dependence pragmas, okay, so in the HLS dependence pragmas, you can tell the tool that there is dependency is not there. Okay, so just ignore these two lines. So for example, here what I have added, HLS dependence pragma, on which variable? It is the hist variable. Inter means between the different iterations of the loop, that is the read after write dependence, and I'm saying that the distance is 2. That means what I'm saying that consecutive iterations, you may not be reading and writing from the same locations. That's what I said, x0 and x1 are not same. So I'm telling, using this pragma, I'm telling the tool that in the 2 iterations of the loop, consecutive iterations of the loop, you are not going to read from the same location of the hist of hist array. Okay, that means you can start the next iteration as early as possible or in the subsequent clock cycle. Okay, so by using this HLS dependence pragma, you can inform the tool the information available to you about the dependence. Okay, this is the way you can inform. But you need to understand that here we have made the observation, or we have made the assumptions on the input data that the subsequent consecutive samples or consecutive pixels of the image are not identical. So this is the additional information we are giving to the tool. This may be true in some cases, this may not be true in other cases, but this is the customer is giving us this additional information, and we can use this information to optimize our tool further, our code further. So it may happen that this is not true, because the x0 may be equal to the x1, because your data is coming from any location, and we can't guarantee all the time that the x0 is not equal to x1. So in that case, this code will not work, and you need to come up with some other way to optimize your code. One possible solution is the array partition. What is the array partition? What you can do is that you can divide this hist array into the individual registers, and since they are implemented using the flip-flops, your read and the write can happen immediately, and you can reduce the initiation interval. So by using the array partition, you can avoid the this issue. But the problem with the array partition is that it will lead to the huge increase in the resource utilization. And also, since it is output array, you need to have the local hist variable. And after you complete the scanning of the entire input one, then you need to write another for loop to copy the local hist to the your original hist output. Okay, So that these are the things you need to take care. So array partition is also one possible solution, but it is may not be efficient, but it's a solution. Okay, that can be a one possible solution. What can be the another solution? So now if you look at the histogram example, you can see that there are two cases. In the one case is that where you are reading the values of the input and the consecutive values are identical. So when the consecutive values are identical, why you need to write the data into the memory every time? You can just create a local variable and you keep on accumulating until your consecutive values are different. Only when the consecutive values are different, then you can write back the previous value to the your back to the memory. Okay, so one case is when the input contains the consecutive values in the same number or same value. In that case, we can use the simple register to accumulate the corresponding value. So you can see that I'm using this accumulator, and when the old value is equal to previous value, I'm just doing the accumulation of the one. When the second case is that when the input, the consecutive values in the inputs are not same. In that case, what I'll do, I'll write the accumulator back to that histogram one, and then I'll read the new values from the histogram array, and then I'll start accumulating. Okay, so for example, if I get say 4, 4, 4, 5, initially assume that the histogram is 0. When I read 4, I'll get the accumulator as 1. Then I read 4, I'll get the accumulator as 2. Then I'll read the 4, I'll get the accumulator as 3. Then I read 5, they both are not together same. Then what I'll do, I'll take the fourth index from the histogram. I'll update that to the 3. Okay, so I'll write the hist of 3, sorry, hist of say 4 is equal to 3, and then I'll read the current value of the hist of 5. Okay, and then I'll store inside the accumulator. Okay, I'll store the inside the accumulator. So in hist of 5 say initially 0, so I'll store the corresponding 1 inside the accumulator, and suppose that I get 6 here, then I'll write the hist of 5 back to the memory and read the hist of 6. So you can see that I'm not doing the read and the write from the same location in the histogram. But when you write this code, the tool will always see that okay, you are doing the reading as well as writing from the same, from the hist array in the same iteration of the loop, and tool will assume that there is a dependency here. Okay, read after write dependency. So by using the HLS Pragma, you can tell the tool that there is a no dependency. You are telling the tool that the dependency is false. The read after write dependency is false. Okay, so by telling the tool that there is no dependency, you are helping the tool to optimize your code faster. Okay, so now you can see that the tool will know that okay, there is, you are doing the reading and the writing, but here there is a no dependency. You can see that here you are doing the write operation and here you are doing the read operation, but these, you know that the way you have written the code, these two main, it cannot be same at the in the single iteration, but the tool doesn't know. So by using this pragma, you can tell the tool that there is no dependency here. Okay, so in the midsem, we are not expecting you to provide the solution, but at least we were expecting you to identify that there is this dependency is there and come up with some sort of code, something like this, to overcome this dependence. And the similar question was also there in the quiz 2, where fortunately the answer was already there in the slide. Now, can we do it better? Can we improve it further? Okay. So one of the possible solution to improve it further is that you can divide your input data into the number of bunch of data. For example, as we have asked in the midsem, that instead of having the entire input data as a one go, you can divide the input data into the part 1 and part 2, and you can use the two ports to read the input data parallel. So if this option is there, can you do better? So what you can do is that you can find the histogram for this guy, you can find the histogram for this guy, and then you can do the addition of the two histograms. So you can see that I'm dividing the input into the 1, 2, 3, any number of sections. I'm calculating the histogram for this one, this one, this one together, and then I'm just doing it to the merge operation to get the final histogram. For example, if we take the array, say 1, 2, 1, 2, what I can do, I can divide the array into the two part, 1, 2. I can get the two part. From this, I'll get the hist of say 1, which is 1, 1, and then I'll get the hist of say 2, which is 1, 1. So that means it contains the two pixels or two elements of value 1, one each of value 1 and 2. And then I'll get the final histogram, which is the HRS, which is the 1 plus 1, that is 2, 2. So that indicates that my input contains the two element of value 1 and two elements of value 2, and this is what I'm doing. Okay, so via this dividing your input, you can do the you can improve the performance. So for example, you can see that I have the input A, input B, and the output is the histogram. So here you can see that I can use the two HP ports, HP0 and the HP1, to read the two inputs simultaneously. And then I can use the same function to calculate the histogram for the input A, input B, and then I can do the addition of the two histogram to get the output. So addition, you can see that it's a straightforward addition of the two histogram. And here you can see that I can use the data flow. So we are not expecting you to use the data flow, but at least we were expecting you to come with something logic where you can improve your performance. So here the data flow indicate that you can start the histogram map for the second one before the completion of this one, because both of them are independent. So you don't need to wait for the input B to be processed. You don't need to wait for the input A to be processed before starting the processing the histogram for the input B. So both of them can be executed in parallel, and then after that you can start. You don't need to wait for the completion of the histogram map for input A and B to start the histogram reduce, because you can see that once the histogram if the input A map, or once the histogram of input map is done and the input B is done, you can start the histogram reduce function. Okay, so depending upon the dependency, you can speed up the performance. Okay, so there the data flow can be used. So here, most probably what will happen using the data flow, your histogram map for input A and histogram map for the input B will be executed in parallel, and then you will have to wait for the both of the function to be completed before you start the histogram reduce. Okay, so this is how this function will be executed. Okay, so to summarize, we have used the data flow directive here to enable the design with the task pipelining. Okay, so here we have the total three processes. One is the histogram for the input A, histogram for the input B, and then the sum of the two histogram. Now here we can see that within a single task, we can have the histogram process for the input A and input B can be executed concurrently, because they are working on the independent data. While the histogram reduce function, or the sum of the histogram sum function, needs to be executed after it completes the histogram map function execution is completed. So data flow directive, it creates a two task pipeline. Okay, so you can see that it can have the input A here, then input B here. You are calculating the map function in parallel. Okay, and then you have the summation is happening here, and you can see that these are the two-stage pipeline. So where the first stage is you are doing the partial histogram, and in the second stage you are doing the what you say, the histogram addition or histogram reduction. Now, what is the initiation interval of this entire histogram function? So how fast this entire histogram function can be called? Now it depends upon the suppose this is the x1 time and this is the x2 time, then it depends upon the maximum of x1 and x2. Okay, because you know that the output of this one will be used by this one, so your initiation interval of the top level histogram function will be the maximum of the initiation interval of the map function or the radius function. And what is this map function? Radius function is nothing but the sum of this one. The map function is nothing but the same as the one which we have discussed before. Only thing is that you need to make sure that your histogram array is initialized to 0 in the beginning, because you are calculating the histogram of the new one. And if you look at the dependence, what we are saying, the intra-dependence of this is false. Okay, that is, this dependence is false, which is same as the previous one where we say that the intra-dependence is false. Okay, so this is how you can implement the histogram calculation efficiently in the memory, in the SDSoC. This will be the part of the quiz 3, where you will be implementing the histogram calculations of the image, and you will optimize it in the SDSoC. So we have discussed the HLS latency, we have discussed the HLS data flow, and we have discussed the HLS dependence. There are 4 other pragmas, which are the loop flatten, loop merge, and the loop drift count, and the HLS inline. These pragmas will be the part of the, again, the quiz 3, which is the take home quiz. So now in the next video, we will discuss about the implementation of the FFT algorithm using the SDSoC.